Welcome back to the future. Today, I'm Mark Dying, your guide to what's next in tech, and maybe a little obsessed with it.
And I'm Jenny, here to, ask the practical questions. Mark, you're practically vibrating. What's gotten into you?
Jenny, we are finally, living in the future. For 20 years, scientists have been hyping graphene as this miracle material for electronics, and for 20 years we've been waiting. Well, folks, it's 2025, and the wait is over. Really, truly over.
Okay, hold up. The miracle material. That can't actually do the thing it needs for computers, right? The bandgap problem? I thought that was the big hurdle. The thing that kept it in the lab.
Exactly. The zero bandgap problem. Graphene is superconductive, but you can't turn it off, which you need for a semiconductor to work. Think of it like a light switch that's always stuck in the on position. But get this. Researchers at Georgia Tech have finally created the first functional time semiconductor made entirely from graphene. Not just a tiny flake, but something real.
Okay, actually functional? Not just a lab curiosity. Another, next big thing, that never quite makes it?
Actually functional. And here's the kicker. It allows electrons to move 10 times faster than in silicon. 10 times. Walter DeHeer, one of the lead researchers, put it this way. Quote, "It's like driving on a gravel road versus driving on a freeway." Quote. And let me tell you, we have been on that gravel road with silicon for a while now.
Okay, that's a pretty compelling analogy for speed. So, terahertz computing? Is that what we're talking about here? Because that sounds, fast. Like sci-fi fast.
Oh, we're talking terahertz, Jenny. Silicon has been hitting its limits, right? We're squeezing more and more onto chips, but the laws of physics are catching up. Graphene just opened that wide open. Imagine devices operating at 500 plus gigahertz frequencies, generating 90% less heat. That's like going from a clunky old desktop tower to something sleek and silent.
That's wild. Less heat means smaller cooling systems, possibly faster phones, and maybe even quantum computing components? Like the interconnects for those super cold systems?
You're reading my mind. This isn't just about faster smartphones. It's about the foundation of next-gen computing, quantum resistance, AI processing, 6G infrastructure. It all gets unlocked by pure speed and efficiency. And it's not doping. That was always the tricky part. This is pure graphene, doing the heavy lifting. It's elegant in its simplicity.
So if the tech is here, what about making it? Is this still something that's super expensive and hard to produce like we used to hear? Because I remember stories of making it atom by atom, practically.
Oh, this is the second part of the story, and it's equally impressive. In 2023, producing graphene via chemical vapor deposition, or CVD, cost around $100 per square meter. Fast forward to 2025, it's down to $30 to $50 per square meter. That's a 50 to 70% reduction in just 2 years. That's like a new smartphone, costing half its price in 2 years. It just changes everything.
Wow. That makes it much more appealing for industrial applications. It goes from curiosity to commodity almost.
Exactly. And it's not just cost. AI-driven defect control has pushed defect rates down to less than 0.1% at wafer scale. That means it meets semiconductor industry standards. It's production ready. We're talking about roll-to-roll continuous processing here, like printing newspaper, but with atoms.
So we're actually seeing graphene foundries, stamping these things out now? Not just small batches in a university lab?
Yes. The European Commission's 2DEPL project, it's essentially a graphene foundry. They're integrating layered materials into standard semiconductor platforms. Amaya Zurutuza from Graphene in Spain mentioned that transfer is not the main bottleneck anymore. Quote, "They've mastered getting graphene onto 200 millimeters wafers, compatible with existing fabrication lines." That's a huge deal, Jenny.
That's huge. Because compatibility with existing infrastructure is always a major cost and time barrier for new materials. You don't have to build a whole new factory from scratch.
Precisely. It means OLED electrodes, advanced sensors, and even some initial computing components can start rolling out without needing to build entirely new factories. It's a true industrialization tipping point. Graphene is finally leaving the lab and entering our lives.
It sounds like we're finally at a place where Graphene isn't just a science experiment, it's a real-world material. And you mentioned medical applications? That always sounds a little spooky, but also promising.
This is where it gets really impactful, and honestly, a bit mind-bending. Imagine a device that can predict an epileptic seizure 15 minutes before times it happens. Graphene brain sensors are doing that, even detecting low-frequency changes that old electrode arrays miss. Think about the peace of mind it gives to someone and their family.
15 minutes? That could change lives for people dealing with epilepsy. That's not just predicting, that's giving back control.
Precisely. And for Parkinson's patients, companies like INBRAIN, Neuroelectronics, are using graphene FETs, field effect transistors, as neural implants. Early trials show a 40% reduction in motor symptoms for Parkinson's patients, and significantly reduced inflammatory response compared to traditional metal electrodes. The EU particularly has been funding this through the Graphene Flagship program for a decade, and that long-term investment is really paying off. They're really leading the charge in medical devices, not just the manufacturing.
That's incredible. But, and this is where my curiosity alarm bells start ringing with brain-computer interfaces, what does this mean for privacy? If these devices are sensing brain activity at a single neuron level, that's a lot of data, like a times lot, times a lot.
It's a critical question, Jenny. Graphene's ability to pick up such fine-grained neural signals raises entirely new ethical dilemmas. What if this data reveals our emotions, intentions, or subconscious biases? Ethicists are already warning about brain hacking scenarios, especially if commercial entities get involved. Imagine your internal monologue being readable.
Right? My thoughts are private, thank you very much. Does GDPR or any other frameworks even cover neural data yet? Because it feels like we're way ahead of the legal system here.
Not specifically, not comprehensively. Companies like INBRAIN are implementing on-device encryption, but industry-wide standards are voluntary at best. It's an area that needs urgent attention as these devices move beyond clinical trials and into broader use. Who owns your thoughts, right?
So on one hand, amazing medical breakthroughs. On the other, a potential Pandora's box of privacy issues. Speaking of ethical considerations, what about the environmental impact of all this graphene production? Are we just trading one problem for another?
Another great point. Traditionally, graphene production used some nasty chemicals, like toxic oxidants. But the industry has moved towards green CVD processes, electrochemical and laser-assisted methods that reduce wastewater by 80%. That's a huge improvement, like swapping out a dirty old factory for something much cleaner.
80% less wastewater sounds promising. But is it energy hungry? Are we powering this new era with clean energy, or just plugging into the same old fossil fuel grid?
CVD still operates at high temperatures, around 1000 degrees Celsius, so it is energy intensive. The key is ensuring that energy comes from renewable sources to keep the carbon footprint down. That's the next hurdle for large-scale adoption, making sure the energy backbone is green.
And what about beyond just manufacturing? What happens to the graphene electronics when we're done with them? Is there a plan for recycling? Because that's typically where new materials fall short.
That's a nascent area, I'll be honest. The recycling infrastructure for graphene is still developing. While the EU has directives promoting it, we're not seeing widespread solutions yet. So it's definitely a pro and con situation on the environmental front right now. A bit of a mixed bag.
It sounds like we're staring at a future where traditional silicon-based electronics are going to hit a wall, and graphene is set to smash through it. But how does this play out, practically? Are we just going to swap out silicon for graphene in all our devices like a simple upgrade?
It's not a direct one-for-one swap, at least not immediately. Silicon still reigns for digital logic because of its on/off ratio. Graphene's on/off ratio is still a bit modest, about 1000 to 1, compared to silicon's 1 million to 1. So silicon is better at saying on or off very clearly. But here's the clever part. Hybrid chips.
Hybrid? As in marrying silicon and graphene? Like some kind of tech wedding?
Exactly. You use silicon for the parts it does best. The digital processing, the heavy logic, the brain of the computer, and then you use graphene where it excels. For ultra-high frequency applications like 6G communication, quantum computing interconnects, and ultra-low power analog circuits, it's like having specialized Olympic athletes for different events.
So, silicon for the brains, graphene for the speed and communication elements? That makes sense, playing to each material's strengths.
Nailed it. And graphene's thermal conductivity is off the charts. 5,000 watts per meter Kelvin compared to silicon's 150. That means devices can be packed much denser without melting down. Think about super compact, powerful hardware that doesn't need huge fans. Your laptop could run silently, or data centers could shrink.
Which is critical for things like data centers or complex AI systems that generate so much heat. That's a compelling future. So summing this all up, Mark, where does graphene stand in 2025, and what can we expect in the next few years?
In 2025, graphene has decisively moved from the lab to industry. The breakthrough in functional graphene semiconductors, coupled with massive drops in production costs and advancements in defect control, has opened the floodgates. We're talking terahertz processors, truly tiny and efficient sensors, and medical devices that can interact with the human body at an astonishing level. It's here, it's real.
And the investment seems to reflect that confidence, right? Money talks, as they say.
Oh, investment. We saw an incredible $2.1 billion in venture funding for graphene in 2025, which is a 300% jump from 2023. That kind of money doesn't lie. While we still need to tackle ethical frameworks for neurotechnology and refine those on/off ratios, I anticipate within the next 5 years, graphene electronics will transition from specialized applications to integrated hybrid systems that redefine what's possible in our daily lives.
So, no more gravel roads for our electrons, just super highways. I can't wait to see what devices come out of this, and maybe, just maybe, what new ethical debates it sparks. Thank you, Mark.
Always a pleasure, Jenny. And thank you, listeners, for joining us on this dive into the new era of electronics. What do you think about graphene's future? Let us know on social media. We are at The Future Today Pod. We'll catch you next time on The Future Today.
Until then, stay curious, and maybe keep an eye on those brain-computer interface terms and conditions.